Okay, so now we're at the last part of our quadratic unit here. We're going to be looking at graphing these quadratics. So take a look at what we have. Learning objective wise, I can find the axis of symmetry and the vertex for these quadratic graphs. I can predict the opening of these quadratic equations by looking at the A value. So let's define a couple of things here to get started. This is what a quadratic graph looks like. It's a U-shaped parabola is what you call it. Parabola, quadratic equation graph. U-shaped. Now, there's a couple of key things that's going to help us graph this stuff that I want to introduce you for today. The axis of symmetry is pretty much what it is. If you looked at axis of symmetry and you knew its definition, that's exactly what it is. You're looking at axis, which is kind of the middle of a piece that keeps it all balanced, and then symmetry tells you it's symmetrical on one side or another. It's the same distance away from this axis of symmetry, one side or another. So basically, this axis of symmetry cuts your graph in half, and you have the same pieces on both sides. Now, the vertex, the other important piece, that was axis of symmetry. Vertex, the other important piece we're looking at today, that's either the minimum or the maximum, depending on which way your graph's going, of your graph. It's the turning point, so to speak. So if you have that U-shaped graph, it's where it hits the bottom and then starts to turn back up. It's its turning point. It's vertex. Couple of other key points to look for would be intercepts. They really help you when it comes to graphing because intercepts are kind of easier to find than other points because you're plugging in a zero. If you're looking for y-intercepts, you plug a 0 in for x. If you're looking for x-intercepts, you plug a 0 in for y. But that's the nice thing about the x-intercepts. We've been finding them for the last like 2 or 3 weeks. We've been finding them for the last while by dealing with those different methods. So if you can find solutions, you can find your x-intercepts and you can match it with that graph there. I want to show you one last thing before we get to the next page. But when we're looking at axis of symmetry, the thing that cuts it in the middle, right? To find that, you're going to take the second coefficient. You're going to take the opposite of that second coefficient and then divide it by 2 times the first coefficient. Negative b divided by 2a, axis of symmetry. Then you're going to use that value to find the vertex because your axis of symmetry is the x value of your vertex always, 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 always. And then you take that value and you plug it into your function to find the y value, which tells you exactly where that vertex is. So axis of symmetry, very crucial. It tells us the middle of our graph. We could use it to find the vertex. And then once we have the vertex, guys, we're pretty much set. Find a couple of intercepts or a couple other points, graphs are done. Now, today we're not going to graph the whole thing. We're just going to like intro it. Okay, so we're only looking at axis of symmetry and vertex. And we're also looking at the opening of these equations by looking at the A value. Let me show you what I mean by that A value. That A value, let's say we had a typical quadratic where it's A x squared plus bx plus your constant c. This is where we get these different values. A is your coefficient with the x squared term. B is your coefficient with the x term. C is C for constant. No variables with the constant at all. The x squared being the biggest exponent, it really tells you a lot about your graph. It tells you if it's going to go up or if it's going to go down. It tells you if it's a little wider or if it's kind of normal or if it's skinnier. So let me talk this up a little more. If your A value is positive, if you have a positive x squared, your graph's going to end pointing to the top. And it doesn't have to go through this point. It could go through something like this. It could go through something like this. It could go through something like that. All that matters is that it's going up. You know what I mean? Positive goes up. Negative, the exact opposite. The end points of the graph are going down. So it's like a backwards U going down. And again, just like with a positive one, it could be anywhere, but you always know for sure it's pointing down. Now, when you have A values between 0 and 1, your 1/2s, your 0.1s, your 0.25s, your 1/8s, your fractions that are smaller than 1, your decimals that are between 0 and 1. These coefficients means your graph gets wider. The way I want you to think of these ones here, guys, this A value, I want you to relate it back to slope because it really relates back to slope and how it moves and what direction it goes. Positive slope, okay, it went up. Negative slope, it went down. When I had fractions or decimal slope, it went wider. For example, I went up 1 over 2, up 1 over 2, instead of just 1, 1, 1, 1, 1, 1, 1, 1. You know what I mean? So it could be really wide. It could be just a little bit wider. But your fractions and decimals between 0 and 1, wider graphs. Now, if it's 1, it's going to look pretty straightforward. Wherever your vertex is, you could count just 1 and over 1 on both sides, and it'll look like this. The only reason I say normal or typical or regular is because it's the value that shows up more often than not. Especially at our level of working with quadratics, you might see a lot more x squared with that invisible 1 coefficient. Now, if it gets bigger than 1, you would think it gets wider, right? But if we relate it back to slope and we had a slope greater than 1, that's where it started to get skinnier. So instead of just going up 1 over 1, it would be like up 4 and over 1, up 4 and over 1 other direction. So you're getting skinnier with your graphs. Oh man, if I could. Oh, that's a terrible graph. Does that make sense? Your slope is getting skinnier. Your slope is getting steeper, which causes your graph to get skinnier. Where if your slope is getting longer, it causes your graph to get wider. So there's your quadratics. Looking at axis of symmetry, vertex, and then our A value to predict these different points. Let me show you some of this delta math. Now, the delta math that deals with this A value is going to be very straightforward. You're really just going to be focused on whether it's going up or down, positive or negative, and then you're going to match the graph to your A between 0 and 1, your A equals 1, and your A greater than 1. So take a look at this one. Oops. There's 3 graphs that you have to match with these 3 different values. You have A equals -1, A equals 0.25, and A equals 4. Now, negative means it has to go down. That's the only one going down. It has to match with this one. See how I just dragged and dropped? 0.25 versus 4. 0.25 is that number, that fraction decimal between 0 and 1. That's going to be a little wider. 4 is that number greater than 1. That's going to be a little skinnier. We're going to look at something like this here. Look how much we can do just by looking at that A value. We can predict how this graph is going to look. Try another one. Just really quick. A equals 1.5 and 4. They're all positive, but now we got to try to match them up. Looking at these 3 different graphs, I have one that's kind of skinny, a little wider, and one in the middle. So let's put this one in the middle with the 1. Let's put the skinnier one with our greater number than 1. There we go. And then let's put our graph that's a little wider with the decimal between 0 and 1. Thinking about that slope, I have a slope of 1, I have a slope of 4, I have a slope of 1/4, I have a slope of 0.25. predicting A values. So that's half of the delta math. Now the other half is going to be your axis of symmetry and vertex. Be very careful here. They tricked me with this once or twice. Make sure you look at what they're asking for. This one's asking for the vertex. Sometimes they ask for only axis of symmetry, so be careful. But with this one, we want to find the vertex. So we're going to plug in the A value and the B value into our equation. 4x squared, 16x, 36. 4x squared, 16x, and 36. Now, guys, it's going to help to have a calculator, especially with some of these ones. But we'll do what we can. Now, remember, it's negative b divided by 2 times a. So what that means is we want to take our b value and put the opposite of it. It's positive, so I put it as negative. Then I take the a value and I times it by 2 on the bottom. My a value is 4. So I have negative 16 divided by 2 times 4, which becomes negative 16 divided by 8, which becomes negative 2. So there's the x value of our vertex. There's the axis of symmetry. But we want the vertex of this graph, which means we also need the y value. So what we're going to do is we're going to plug this axis of symmetry, this x value, into our equation, simplify, and get the y value of our vertex. So if I'm looking at this one, we had negative 2, right? So every time I see x, I plug in negative 2, and then I simplify. Some of us might be able to do this in our heads, at least pieces of it, which is good. Makes it a lot faster. Otherwise, just use calculator. Makes it just as fast. But negative 2 squared becomes 4. 4 times 4 becomes 16. 16 times negative 2 becomes negative 32. Negative 32, then that plus 36. I'm going to combine these 30s together. Negative with positive is subtracting. 36 minus 32 becomes 4. So I have 16 plus 4, which equals 20. So my vertex is this x value and this y value together. So I could write that in my parentheses, negative 2, comma, 20. Negative 2, comma, 20. Vertex. It's a good thing we don't have to graph that one. That'd be a big graph. But negative 2, comma, 20. Axis of symmetry, plug your values in. There's your x. Plug it into your equation. There's your y. So you have your vertex. I've checked it on Delta Math. They will not accept it without the parentheses for vertex. So make sure you have those parentheses, and then you should be good to go. Intro to graphing our quadratics, guys. Let me know if you have any questions.